Okay, welcome back students to 7.3. This is all about the equilibrium constant and reaction quotient. We talked a little bit about this on Thursday last week as well as Monday this week, but we're now going to go into a little bit more detail about what each of these two letters here, or each of these two concepts are. Now let's start with the most common one. That's going to be the equilibrium constant K. And the thing to understand about K is that when a reaction reaches equilibrium at a certain temperature, because these reactions are often temperature dependent, but when it reaches equilibrium at a certain temperature, there will be a ratio of the concentrations of product to reactants. It'll be a very certain ratio of concentrations of products to reactants that is unique for that particular reaction. Whatever this ratio is, we call the equilibrium constant. And I have a general reaction right here where lowercase a represents, or all the lowercase letters represent the molar coefficients that you would find in front of the substances, and the capital letters represent the actual substances themselves. So to write an equilibrium expression, you would start off with Kc, which is the equilibrium constant, the letter for equilibrium constant. And it is the product, or you achieve this or solve this by multiplying the products of the reaction together, the concentrations of the products, and each product is raised to its molar coefficient, the power of its molar coefficient, and then you will divide that by the reactants. So you will multiply both reactants together and then raise them each to their molar coefficient, the power of their molar coefficient. You can only write an equilibrium expression if and only if the substances in question are either a gas, an aqueous solution, and the concentrations that the problem gives you, or the concentrations that it asks you to solve for, are at equilibrium already. These three requirements must be met in order to write an equilibrium expression. Let's go ahead and do an example problem here. We have 2 moles of nitrous oxide gas in equilibrium with 1 mole of dimer dinitrogen tetraoxide. At equilibrium, it says the concentration of NO2 is 3.64 molar and the concentration of N2O4 is 2.56 molar. What is the value of the equilibrium constant? Now, even though these are gases, for whatever reason the problem gave us concentrations instead of partial pressures, but we can still work with this. Okay. First thing you do is determine what is this question asking us to find. The question is literally asking what is the value of the equilibrium constant. So we are looking for Kc. Let's go ahead and write an equilibrium expression. Kc. And that is going to be equal to the products. And there's only one product here, so that's kind of nice, which is N2O4. So the concentration of N2O4 raised to the power of its coefficient, which is just 1, because there's implied to be a 1 there, but we don't show 1s in AP Chem. And then we're going to divide that by the concentration of the reactants. There's only one reactant here, that's nice, so the concentration of NO2, and we're going to raise that to the second power since the molar coefficient out in front is 2. Now that we have our equilibrium expression, let's look back at the problem and make sure that the concentrations they gave us are at equilibrium. And if you read the problem, the very first sentence says, at equilibrium, the concentrations of NO2 is 3.64 molar, and then the concentration of N2O4 is 2.56 molar. So these concentrations are at equilibrium. We are at liberty to solve for the Kc expression. So let's go ahead and plug in our numbers. 2.56 for the N2O4, and then we have 3.64 raised to the second power for the NO2. I'm going to go ahead and figure out what that bottom number is in my calculator here. So the bottom number to 3 sig figs is 13.2, and let me verify that. One more check. Yeah, 13.2. And then we're left with 2.56 on the top. We divide. And we get an equilibrium constant of 0.193 to 3 sig figs. So that's the equilibrium constant. If you wanted to write it in scientific notation, you could, because oftentimes equilibrium constants are given in scientific notation to be 1.93 times 10 to the negative 1 power. But this will suffice. And notice that there are no units with the equilibrium constant. Okay? Equilibrium constant is a unitless number. Alrighty, let's go ahead and take a look at another example problem, and this time it's a little different. According to the reaction below, 0.14 molar of NH3 is in equilibrium with 0.020 molar N2. What is the equilibrium concentration of H2? Okay, so the reaction up here is N2 reacting with 3 moles of H2 to produce 2 moles of NH3. The problem said that we have this much, we have NH3, 0.14 molar NH3 at equilibrium, and then it said we had 0.02 molar N2 at equilibrium. And then the question is asking us to find, well, what is the concentration of H2 at equilibrium, right here. And then it gave us the Kc already, the equilibrium constant, which is 1.7 times 10 to the second power when the reaction's at 225 degrees Celsius. This information is not that important right here, it just gives it to us in this case. Okay, so this is still an equilibrium problem, so we're going to need to start off by setting up an equilibrium expression. And let's check to make sure that we can use all this up here in the equilibrium expression. First and foremost, is everything either a gas or at aqueous phase? It sure is. Everything is already a gas. So that's one check there. Are the concentrations that they give us already at equilibrium? And yes, they are. If you read the question, it says, according to the reaction below, the 0.14 molar of NH3 is in equilibrium with the 0.02 molar NH2, or the N2. So we met that requirement there. Okay? Let's go ahead and write our Kc expression. So it's always products over reactants. We have one product again. That's really nice. Raised to the second power, since the molar coefficient out front is 2. This time we have 2 reactants, okay? So it's going to be the concentration of N2 raised to the power of its coefficient, which is just 1. We're going to multiply that by the other reactant, which is H2, raised to the power of 3, since the molar coefficient out in front is 3. So here is our equilibrium expression. Now again, unlike the last problem, we're not solving for Kc this time. We're solving for H2. So we need to manipulate this equation algebraically to get the H2 by itself. Now I assume you know how to do algebra. But in order to get the H2 by itself, the first thing I'm going to do is flip the reaction. So now I have 1 over Kc, or flip the expression I should say, because we want to get the H2 by itself. And the H2 needs to be on top. It's not necessary to show all of your algebra steps on the AP exam, believe it or not. And then we need to move the N2 over to this side, and we'll have to divide that, so that'll end up on bottom. And then we need to have the NH3 over on the other side, so that'll end up on top. So that means the concentration of H2 cubed, okay, is going to be equal to the concentration of NH3 raised to the second power over the concentration of N2 times Kc. Now, this still isn't by itself. We have that to the power 3 there. So if we take the cubed root of both sides, and again, I just assume you remember how to do your algebra, that means we're going to have a final expression of the concentration of H2 being equal to the cubed root of the concentration of NH3 squared over the concentration of N2 over the concentration of N2 times Kc. Alrighty, kind of a lot to do there, but let's go ahead and now we have our expression. Everything is set equal to H2, so let's go ahead and plug in. And you will for sure need your calculator here. Alright. Quite a bit of math to do in there before we take the cube root of anything, so let's do that. 0.14 raised to the third power is going to be 0.0027, two significant figures, and then we have 1.7 times 10 to the second, which is the same thing as 170. Times 0.020, that's 3.4 on the bottom. If we divide those and take the cubed root, we end up with 0.093, let me make that neater, 0.093, that's the concentration of H2. Now I do need to have a unit with this one because I'm solving for the concentration of H2, and concentration is in units of molarity. Alright. So that's that problem there. Please pause and rewind the video if you need a repeat of that. But for the reaction quotient, I'm not going to go into too many problems about solving the reaction quotient because it is quite literally the same way as K, it's just the parameters are different. The reaction quotient is very similar to K, but it is used when the reaction isn't at equilibrium, or if it is unknown if the reaction is at equilibrium. So you would set it up the same exact way you would a K expression. You would just replace the K with a Q equals. And again, the requirements are pretty much the same. Still needs to be a gas or at an aqueous solution, but this time the concentrations can be at any point in the reaction. So if they don't specifically tell you it's at equilibrium, or they say that the equilibrium is unknown, then you need to be thinking about the Q, okay, the reaction quotient. And again, it is calculated the same exact way as K, it's just the parameters are different. Okay. We will often only calculate Q when we need to compare it to a known K. So that'll go ahead and do it for 7.3, ladies and gents. Go ahead and try the questions that follow, and we'll see you in the next video.